Hi, okay, and in this video we'll go through the VSEPR theory, so finishing off the AS set fully since I haven't done anything for use for a while. Right, so first off you are going to need one of the tables showing all the various shapes and bond angles, so I'll flash one up on the screen now, but you've probably got one printed off. Right, and in going through this theory there's three things what you're going to need to be able to do, so I've put them there. The dot and cross first, that'll be helpful because then you can quite clearly see the bonded clouds of electrons and the lone pairs. So we're going to be needing to count those on the central atom only. And then obviously the third thing is being able to use your memory, because you're not going to get that table in the exam. You do need to actually remember all the shapes. So yes, that sucks. Right, now obviously the dot and cross, I'll go through the Lewis way of actually doing it. Some people can just more or less look at the compound and get it done in their head quite quickly if you've had some practice at GCSE. So I'll go through a example molecule or compound for all of the various shapes, and as I said I'll do a dot and cross example for some of them as well in full. Right, so here we've got carbon dioxide. So this is pretty much your block basic linear compound. So as we can see there, we've got the CO2, obviously the carbon, it's got its octet. Each of the oxygens have got its octet here. So if I need to count up all of the things around the central atom here, well, carbon, it's got no lone pairs. The double and treble bonds you just count as one. So one sort of electron cloud there basically. So 1, 2, we've got two clouds. So if you look at the table, go down to the VSEPR number 2 on the left hand side. Obviously we can't have any lone pairs with this, otherwise even if you did it would just be sort of two things. And then as you can see you've got a linear shape with 180 degrees. Now if you're struggling actually getting this dot and cross diagram for CO2, I'll show you how to get that step by step now. Okay, so here we've got the carbon dioxide. You can print off a written copy of these rules, plenty of places on the internet if you just search it up, the Lewis dot and cross. So I'll go through where I've got the numbers from and obviously how we've got these trial and final. I'll do a couple more rather than CO2 as well later on when we're looking at some of the others. So where I've got this 16 from? Well, you need to add up the total valence electrons for them all. So carbon's in group 4, so that's where the 4 comes from. And we've got two oxygens, so oxygen's in group 6. So obviously 6 times 2 for those is 12, plus the 4 from carbon gives us the 16 electrons. Now if I had any negative charges, so say this was CO2 2 minus, then you add 1 electron for each negative charge. And vice versa, if you had any positive charge, then you would take 1 electron away. So that tells you the total amount of electrons you've got to play with in actually putting this structure together. So the next thing to do is make an actual trial structure. So obviously everything's got to be bonded to each other. Now carbon will typically be your central atom in all of the compounds what you're looking at, because it forms the most amount of bonds. So we put carbon in the middle, we'll form one bond to each of the oxygens on the outside here. Now that still gives us some electrons to play with, because obviously we'd have only used 2, 4, so we'd still have 11 to go. Now things must meet the octet rule. Everything bar hydrogen. So hydrogen obviously just needs the 2 electrons. So oxygen needs 8. So if it's only got 2 here, then we need to fill it up with the remaining electrons. So 2, 4, 6, it's at 8 now. And across here, 2, 4, 6, 8, that's also at 8. So if you counted them up now, that's all 16 electrons used for us. If we had any more electrons still spare to play with, then you would have added them onto the central atom. Now as we can see though, carbon isn't happy there, it's only got 4 electrons. Carbon wants to meet the octet as well. So what we do to get the final structure is a bit of jigging about, because as we can see here, what we can do is we can take 2 electrons from this and we can form a double bond in there. So forming a double bond, that would have taken carbon up to 2, 4, 6. but again, still not at the 8. So go to the other side, we can do the same. So if we take 2 off there and form a double bond on this side, now everything meets the octet. Each oxygen, 2, 4, 6, 8. The carbon, 2, 4, 6, 8. And there is your dot and cross for carbon dioxide. So as I said, that's a linear structure, 180 degrees in there. Okay, so moving on to the VSEPR number 3 here. So BF3, fairly standard compound, usually doesn't go round like this because as we can see here, the boron isn't meeting the octet rule, so it tends to be either joined up in sort of B2F6, same as you might see Al2Cl6, or you could have some sort of dative covalent bond form there. But you should be able to sort of work out again, just sort of looking at the central atom here. So we've got no lone pairs of electrons, but we've got 1, 2, 3 bonded clouds there. And effectively, if you look at your sheet with the shapes on, just go down to VSEPR number 3, obviously 0 lone pairs, so you would just stick in that first column. And as we can see, we get a trigonal planar shape, 120 degrees. So effectively it's like a flat circle that you've cut up into 3 equal pieces. Because what the VSEPR theory is, since I didn't mention it, is the valence shell electron pair repulsion theory. Effectively it just states that, well, electrons are negatively charged, so electrons want to be as far apart from each other as possible. So as we can see here with these 3 electron clouds there, 120 degree spacing between them, that's as far apart as they can possibly get from each other. Now moving across onto the next column, so we're still in the total VSEPR number 3. So the total VSEPR number is when you add the bonded clouds with the lone pairs. So obviously 0 lone pairs plus 3 gives you the VSEPR number of 3. And we're going to do the same down here because remember this double counts as 1. So 1, 2, total VSEPR number is 3. But it's got a slightly different shape. It's bent in this case. The reason why is we'll come on to with a few more examples. Lone pairs, they repulse bonded pairs more than bonded pairs repulse each other. So what's happening is this is exerting quite a high pressure squeezing down on both these sides. There isn't as much repulsion in here. So these get crushed together a little bit. Now if you're looking for some of the shapes which appear less often, this will probably be one of them because I'm having a total mind blank trying to think of any molecule that I've seen appear in exams that matches this. So I know ozone does, but it's fairly complex for an AS standard. You could do it just similarly going through the Lewis method, which I've just done. The positive and negative you probably wouldn't really need to care about because obviously the overall thing is neutral. So if you'd had your central atom, obviously it would only have had the 2, 4, 6 electrons since you'd have had both of the outsides meeting the 8 and then just one of them forming the double bond in there. And then you could get the shape from that. Likewise, the angle, I'm not sure exactly what the angle is. I'm taking a guess. It's going to be slightly less than 120 because obviously this is crushing this area together a bit and you're measuring the angle between the atoms here. So I've taken a guess at 117.5 there. So as I said, that's probably one which is going to appear less often, but if you're showing a compound, you should still be able to remember that shape if it's got 2 bonded and 1 lone pair. Right, on to some others. Okay, so on to the VSEPR number 4 here. So again, I'm going to look at some of the favourites. So we've got methane first of all for the tetrahedral structure. So as we can see around the carbon, we've got 1, 2, 3, 4 bonded clouds there and no lone pairs as well. So that would take a tetrahedral structure. So 109.5 degrees because each of these hydrogens are perfectly spaced apart from each other. It's as far apart as they can possibly get. Now I don't have any Molly-Mod kits with me to show you exactly how this is arranged, but the wedge here means that the hydrogen's sticking out towards you. whereas the dashed line means effectively it's going behind the board, and the straight line means these are perfectly flat upon it. So any boys who are listening to this, you're supposedly better because, well, at visualizing the 3D things, because our brains are designed for grunting and throwing spears at slow moving objects with meat on them so we can eat it. Just don't try and use that excuse in a court of law if you have actually thrown a spear at something. As I said, sort of, you can get compounds in an exam which look very similar to it and will have exactly the same shape. So if I just replace these hydrogens, say if I had dichloro-difluoromethane, then all I would do, just chlorine, chlorine, fluorine, fluorine. Makes no difference how you write them round because obviously it's equal spacing. But around the carbon you would still have no lone pairs, 4 bonded pairs. It would be exactly the same shape. So don't freak out if you start seeing things jumbled together that you've never met before. You can usually relate them back to these simpler compounds. Now at the bottom there we can see ammonia, so again that's another favourite. Then nitrogen being in group 5, as we can see here, it's going to have a lone pair because 1, 2, 3, 4, there's the 5 dots, the 5 electrons for nitrogen. Obviously it meets the octet rule now. Hydrogen's happy with its 2 there. So the VSEPR number is still 4 because obviously adding together the 3 plus the 1. But we've got a lone pair, so that lone pair is going to give it a slightly different shape. Same as before, it's pressing down on these 3 hydrogens more than they are repulsing each other. So it squeezes the 3 hydrogens effectively together a bit, which is why the angle is less than up here. So 107 degrees. Now, not all of the trigonal pyramids are 107 degrees. Ammonia is, and you do need to remember that one. If you are asked to predict the angle for ammonia and you just say less than 109.5, you'll not get the mark, because there will be some cocky ass somewhere who just writes less than infinity. Well, technically true, but it's not really predicting a number. If you're asked to predict something for, say, pH3 or ASH3, so the phosphoric or the arsenics instead of the nitrogen, now the angle for those isn't 107 degrees, but you're not expected to remember the angle for everything. Hurrah! But if you're asked to predict it, just give ammonia. So stay at 107 degrees, because obviously if you replace the nitrogen here with phosphoric or arsenic, it would still be exactly the same shape with the 3 hydrogens around it and the lone pair because they're in group 5. Okay, so now looking at water. So this is probably the most famous bent compound. So yes, bent is a name of the shape. You can either call it bent or V shape. Most people at 16 just enjoy writing water as bent on their exam paper just for the giggles. So as you can see, the central atom here, we've got the 2 bonded clouds, we've got the 2 lone pairs. So total VSEPR number 4, just the same as the methane, but the fact that it's got the 2 lone pairs, well, there is a massive repulsion between these. These are repulsing these quite a bit, and it squeezes the hydrogens therefore closer together than in the ammonia. So the angle here, 104.5 degrees. So again, for water, you do need to remember the angle of this one. You can't just write much less than 109.5 degrees. If you're given a compound, say oxygen with 2 fluorines attached to it, then obviously you can just imagine the 2 fluorines here instead of the hydrogens. The shape would be exactly the same. The angle might be a little bit different, but if you're asked to predict it, again, you can't remember every angle. Just stay at water, it's the closest to what you know. Right, now moving on to the total VSEPR number 5. So an example down there, we've got the phosphorus pentafluoride. As we can see here, this is where you start getting onto some of the examples where things are breaking the octet rule. So phosphorus and things like xenon, that'll be a common one. They can use their D subshell, so some of the electrons get pushed up into that. So as you can see around the phosphorus there, there's actually 10 electrons. If you use the dot and cross method, which I said earlier, then again it all still fits in. If you work it out, you've got the 5 fluorines, so 5 times 7, that gets you up to 35. The phosphorus, well, that's in group 5, so you've got 40 electrons to play with. If you form one bond between the phosphorus and each of the fluorines there, well, that takes up 10 electrons, gives you 30 electrons left to play with. Now obviously you fill the outside first, so you fill the fluorines, you give them their octet, and that uses up, obviously, as you can see, 5 fluorines, each of them needs 6. There's your remaining 30 used up. So the shape for this is a trigonal bipyramidal. So effectively you're going to have, as you can see here, a triangle shape there coming up, so it's going to be a pyramid, and you're going to have 2 of these stuck one on top of the other. So 120 degrees round here, because you're going to have sort of these 3 and a flat circle just cutting out into the same as trigonal planar, just 3 equal chunks there. But then you're going to have 1 fluorine up, 1 fluorine down, so these are going to be 90 degree to these 3, which are in the same sort of plane. Okay, just going to run through one of the ions, just how you actually stick it together and where the shape comes from again. So again, going back to it, counting up the valence electrons for each of these. Well, fluorine's in group 7, so 7 times 4. Phosphorus in group 5, so I've added the 5. And we've got a singly negative charge, so I've added 1 here. Gives us 34 electrons total to play with. Now again, the trial structure, so phosphorus I'm going to stick in the middle, it can form the most bonds. I'm going to form 1 bond to each of the fluorines on the outside here. Now fluorine needs to meet the octet, so I've added in enough electrons to put each of those up to an octet. If you count these up, however, so effectively 8, 16, 24, 32, then I've still got 2 electrons spare to play with. So those 2 electrons would get added onto the central atom here. So this is where they appear here. So the final structure, as you can see, is a seesaw structure. Hopefully you can see that it's still got the total VSEPR number 5, because we've got the 4 bonds, we've got the 1 lone pair there. So quite similar to the trigonal bipyramidal. All we've effectively done is taken off one of the atoms and replaced it with a lone pair here. And it's quite similar to when you've got the 3 bonded and the 2 lone pairs. Well, I would just take off another atom there, have a lone pair, and then this is where your T shape comes from. And likewise, if I have 3 lone pairs and 2 bonded, then 1, 2, 3 atoms removed to be replaced with lone pairs, and your linear structure comes through there. So the total VSEPR numbers, the shapes are quite similar, you're just effectively replacing an atom with a lone pair. So this lone pair causes a bit of repulsion round here, so this is why these are squeezed a bit together and those are obviously pushed a bit away. Off the top of my head, I have no idea if this is exactly right for this compound, but taking a rough guess, I know it's going to be squished together a little bit. So in exams there is a bit of leniency, sort of a few degrees area what you can sit within. Normally just knocking a few degrees off, 2 to 3, then that'll keep you in the right ballpark for guessing that. Okay, so what I've got here is 5 compounds. It's 5 of the remaining 7 shapes which I haven't looked at yet. So what I suggest you actually do is just pause the video in a second, have an actual go at working them out, see what shape you think it's going to be, and then I'll write it and you can check. So pause now. And here we have the answers. So I haven't drawn them out, but you should hopefully have the sheet next to you printed off showing the actual shape. So make sure you're actually drawing them quite neat as well, so you can pick up a few marks in the exams. You don't have to be perfect with them, but sometimes the mark schemes do get a bit picky if you're drawing things in plane which actually aren't. Now a good way which actually helps to sort of remember these is to get some study cards kind of like this. Can you see that there? And on one side have the actual name of the compound, and then just turn it over, so have a go at it first, draw what you think it would be, the angle, and then obviously on the other side of the card you just turn it round and check to see if you're actually correct. Or the other way of doing it is just sort of having it drawn out and actually looking at it, being able to say to yourself, what is the shape, what are the angles, and whether or not you can think of a common compound which has that shape. So those are some good ways of actually remembering it. Okay, so questions like these where you're asked to actually compare a compound with sort of an ion version of it. So the ammonium ion here, being able to predict the angles, being able to talk about why there's a difference. Normally people get a bit stumped by it. The fact that you've got 4 hydrogens here but only 3 here. They think, well, surely these ones should be closer together because there's more of them. Well, no, this takes into account, as I mentioned earlier, the lone pair here. So in this shape, just to go through it, it's tetrahedral, 109.5, because we've got 4 bonded pairs around the nitrogen, no lone pairs, so they repel each other equally. Each angle in here is 109.5 degrees. So it doesn't matter that this is a dative covalent, it doesn't take up any more or less space than a regular covalent between these. Across, however, onto the ammonia, so the trigonal pyramid structure here. The angle for this, 107 degrees. Like I said, you must remember the ammonia. The lone pair up here, now the electron density here is higher than across here. Effectively, it's spread out over a bond, whereas this gets condensed into a small region. Because of that, the repulsion between this area is much greater than the repulsion between this area. And likewise, the repulsion between 2 lone pairs is massive. So lone pair repulsion highest, lone pair, bonded pair middle, and bonded pair weakest repulsion. But again, remember there's repulsion between them all. So because there's more repulsion here than there is here, then this lone pair presses down on all of these 3 and squeezes them together. Hence we have a lower angle. And that's just about everything I can think of for the VSEPR theory. Thank you.